Okay, in this section, or these sections, we're going to look at control of solubility. Why is it that sometimes things dissolve together and other times they don't? And so what we're going to look at is we're going to look at first the ways in which the structure of molecules lead to them dissolving or not. That is, how well things mix together based on the intrinsic attractions they have to mix together. And then, secondly, we're going to look at things that we can do to influence that solubility. So we can't influence whether something just wants to dissolve or not, but we can influence how much it dissolves in particular cases. And we'll look at air pressure or gas pressure for gases dissolving, and the effect of temperature on things dissolving in general. So, like all processes, dissolution depends on two factors thermodynamically: enthalpy and entropy. Enthalpy is related to bond strength. And the idea is that stronger bonds represent lower enthalpy, represent more stable. So processes that lead to stronger bonds are favored by enthalpy for thermodynamics. Entropy is defined a few ways, but for our purposes, we actually define it as making things have more freedom of movement. If atoms have more freedom of movement, then they have higher entropy, and that makes things more stable. And what you'll see is that these two things don't necessarily go in line with each other. Enthalpy wants things to stick together. Entropy things want things to fall apart. And the last thing about that is entropy is more important at high temperature. I'll say higher temperatures. And so what happens is if something has a positive enthalpy change, it's disfavored by enthalpy. And it has a positive entropy change. Entropy will want it to be soluble at high temperatures. Enthalpy will want it to not be soluble at low temperatures, so something will be favored to dissolve at higher temperatures. If something has a negative enthalpy change, that means it's favored in terms of enthalpy. Then if it's also favored by entropy, that positive entropy, then it'll be favored at all temperatures. Things will dissolve at any temperature. And if it's disfavored by entropy, then it'll only dissolve at lower temperatures where enthalpy is in charge. And if something is disfavored by enthalpy and entropy, that is this quadrant down here, then it won't happen at any temperature. So let's look at an example. Let's look at just a simple enthalpy and entropy of evaporation. So you have a liquid, and in the liquid, there are IMFs, which are bonds. They're weak bonds, but they're bonds. And so from an enthalpy point of view, the liquid is favored by enthalpy. In terms of entropy, what happens is the gas phase is favored in terms of entropy because things get to move completely freely, whereas in liquid phase they don't. So the gas is favored by entropy. And what we said earlier is that entropy is more important at high temperatures, enthalpy is more important at low temperatures. So the gas phase is favored at high temperatures, and the liquid phase is favored at low temperatures. And that's what we see. Liquids boil at high temperatures, and they turn into liquids at cooler temperatures. All right, and here's a little flow chart for this enthalpy and entropy control. So is dissolution enthalpy favored? You ask yourself that first. Okay, and then you say, okay, if it is enthalpy favored, is it entropy favored? And if it is entropy favored, then it's soluble at all. It'll be highly soluble all the time. And if it's not entropy favored, then it'll only be soluble at lower temperatures. If the dissolution is not favored by enthalpy, you then ask, that means if you're going down this way, you ask, is it entropy favored? And if it's not entropy favored, then it's not soluble at all, and it'll just be insoluble. If it is favored by entropy, then it'll be favored at higher temperatures, because enthalpy is disfavoring it, entropy is favoring it. That's another way of looking at it. Okay, let's look at gas mixtures. So when you have a gas mixture, it's really quite simple. There is no intermolecular forces. So the mixing of the gas has no enthalpy change, because you're not breaking or there are no bonds between the gas molecules before mixing. There are no bonds between the gas molecules after mixing, and so there is no entropy change, no enthalpy change. But when you mix, leads to greater freedom of movement. So on the left-hand side, the blue molecules can only be in one of the containers, and the red in only one of the containers. On the right-hand side, they can both be in both containers, so they both have greater freedom of movement. So it is entropy favored, and enthalpy is like even. So gas mixtures are always favored to mix. Okay. Now let's look at liquid-liquid mixtures. Now it's more complicated. Let's look at mixing water and methanol, which is CH3OH. They both have hydrogen bonds, and methanol has somewhat stronger dispersion forces. Water has stronger hydrogen bonds because it can form more hydrogen bonds because it's got two OH groups. Methanol has weaker hydrogen bonding overall because it only has one OH group. So what happens is, before mixing, methanol has IMFs with other methanol molecules. That's what this is here. And water molecules have IMFs with other water molecules here, largely hydrogen bonds. After mixing, the water has IMFs with the methanols and with themselves. The methanols have IMFs with waters and also with other methanols. So you're breaking some bonds. Waters are losing some water hydrogen bonds. Methanols are losing some methanol hydrogen bonds, but you're forming new hydrogen bonds from the solution that you make. So it's hard to judge, hard to guess the delta H change. So it might be that they're about the same, might be that it's a little stronger, might be it's a little weaker. You can't just look at it and know. Okay, so when two liquids mix, we don't use the term soluble, we term miscible. Two liquids mixing are miscible. Things that do not mix are immiscible. And so we're looking at molecular compounds now, two like neutral molecular compounds like water and methanol. We're not looking at ionic compounds. We'll do ionic compounds later. And the general rule is this: polar solutes dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents. And the chemist's cute phrase for this is like dissolves like. Things want to dissolve in things that are like them. And another example of that is oil and water don't mix. Oil is non-polar and water is polar. And so that leads to oil and water not mixing. So that's the general rule, and it actually is one of the more important rules in lots of things. It's used in the medical field for drugs being said fat soluble versus water soluble. And so oil is fat soluble. So in that range, the term fat means a non-polar medium. And the way we talk about this is we talk about groups either wanting to be around water or not wanting to be around water. Hydrophilic groups are water-liking, which means very polar. And the most important of those are OH groups and NH groups. There are other things that are, but when you look for whether something's going to be soluble in water or not, what you look for are either charged things. If they're charged, they're very likely to be in water. Or you look for OH groups and NH groups because they can hydrogen bond. So molecules like methanol, ammonia, and hydrogen peroxide, all very soluble in water because they can form hydrogen bonds with water. Hydrophobic groups are water avoiding, And the main, most important thing in terms of hydrophobic groups are long hydrocarbon chains. So this is a chain, and it might be linked to something else, but this long chain is hydrophobic in and of itself, even if there's something polar at the end. So examples of this would be 1, 2, 3, 4, 5. This is pentane. So pentane, like all just hydrocarbons, is not completely nonpolar. And this is chlorobutane down here. And it's still also fairly nonpolar, so I would expect that to be not terribly soluble in water because it's got a big hydrophobic group and one relatively small, not all that polar hydrophilic group. Okay, so which of these would not dissolve in water? So this would dissolve in water, or the other way I would say is be miscible with. That will dissolve because NH3's got NH bonds, which hydrogen bond. Methanol we saw earlier, even though it has a small hydrophobic group, the CH3 is a small hydrophobic group, it also has an OH group, so that can hydrogen bond. So that will be miscible in water, it'll dissolve in water, but this will not dissolve. This is ethane, so it will be immiscible in water. And so, because it's fully nonpolar. Okay, which of these will be least soluble in water? So here are three different alcohols, methanol, one propanol, and one butanol. And the idea is each of these has a OH group, a group that will hydrogen bond to water. And the other thing is that it has these hydrophilic groups. And what happens is you go from 1 to 2 to 3, the hydrophilic group gets larger. Larger hydrophilic group. And so what happens is this hydrophilic group leads to it being less soluble in water. So this will be least soluble in water. And one with the smallest hydrophilic group will be most soluble in water. Okay, and so the next thing we're going to talk about is why is it that oil and water don't mix? So the two things, of course, that control this are enthalpy changes, which are changes in bonding, the forces that happen. And the other things is entropy changes, which depends on the entropy change of both the water as well as whatever's dissolving in the water. In this case, we'll talk about oil. So to do this, what we're going to do is we're going to actually look at why they don't mix. And so what we're going to do is we're going to look at an example, two examples, and assume we know why it's happening, and then analyze which of those two explanations seems best. So the first explanation is that the reason oil and water don't mix is that an oil molecule, to mix with water, has to intercede between water molecules and break the hydrogen bonds between the water molecules. So if the water molecule goes between water, if the oil goes between there, it's going to break those bonds. So if that happened, delta H would be positive. It would be disfavored. And delta S would be positive also, and it would be favored because the oil is spreading out, and then the water is also spreading out. So that's one explanation for it. The other explanation is that doesn't happen. In fact, what happens is the water molecules, instead of splitting apart to get to allow the oil to go between them, will essentially envelop the oil molecule and make a cage around it, where the water molecules make a cage. And just like surface tension, what will happen is on the surface of the oil, the water molecules will align themselves in a very specific pattern so that they can be surrounding the oil molecule but not lose their hydrogen bonds. So they don't lose their hydrogen bonds because they essentially lie down flat around the oil molecule and then allow themselves to keep their hydrogen bonds. If that were the case, the delta H, the enthalpy change, would be really small because you're not really breaking any hydrogen bonds. So that would be small. But the delta S would be very negative, which would be disfavored. And it's negative because the water molecules now are very constrained in their motions than they would have been. So those are our two options. One option is that the oil molecules go between, if they were to mix, go between the waters, have to break the hydrogen bonds. That's bad enthalpy-wise, but good entropy-wise. The other one is the water molecules don't give up their hydrogen bonds, but they have to then, on the surface when they're in contact with the oil, have to essentially lower their enthalpy, lower their entropy so that they can keep their hydrogen bonds. In fact, if you do experiments, when you do mix small amounts of oil and water, delta H is actually very close to zero. And delta S, experimentally measured, is highly negative, which then says the correct explanation is that the oil goes into the water makes essentially a cage around the oil molecules and leads to lower entropy. And so that's bad, so it doesn't happen. So the reason oil and water don't mix is because if they were to mix, the water would have to decrease its entropy a lot without any gain in enthalpy, in stability enthalpy-wise. So that's why it doesn't happen. Okay, now we're going to change to talking about, so that's the end of looking at molecular compounds and our whole like-dissolved likes thing. Now we're going to talk about solubility of ionic compounds. And I want to remind you about the solubility rules that you have looked at. And so these are rules for what dissolves and what doesn't dissolve together in terms of ions. So this is not explaining why anything happens. This is just a summary of what happens. And so we just see experimentally that all sodium, potassium, and ammonium salts are soluble. There's one exception to the potassium one, which you may or may not have noticed. In General Chemistry 1, one of the experiments is we make alum, which is an insoluble white solid we make, and that's actually a potassium salt, and we isolate it in water, and because it's not that soluble. So that's an example of where sometimes our rules are don't work, and we show you an example of it in real life and don't even mention it. Apologies about that. But it's really true. Most of them are. In terms of anions, nitrate ions, acetate ions, chlorate ions, which you hardly ever use, and perchlorate ions, which we don't use very much because they can be explosive. Those also are always soluble in water. So those ones are easy. And then we saw that chloride, bromide, and iodide salts are generally soluble, but there's some exceptions to that, like lead chloride would be insoluble. Silver bromide's insoluble. That's one of the main things used in photographic film. Same thing, fluoride salts are generally soluble with some examples of things that don't work that way. And same thing with sulfates. And then for things that are generally insoluble, we have hydroxide salts and oxide salts, sulfide salts, carbonates, and phosphates. Now, the one thing I think that's worth noticing here is that of the things that are generally not soluble, both in terms of our rules for things not being soluble, or our exceptions to things that normally are soluble but now are not, are all things, or not all, but almost, insoluble salts tend to have ions with larger charges. So things with plus all of our salt, all of our ions that lead to things always being soluble, all are +1 or -1. All except for silver plus there. All of the ions that are exceptions to things being soluble and therefore making them insoluble are all things that are 2+. Of the things that are generally insoluble, they're all -2 or -3, except for hydroxide, which is -1. Okay, so we're going to explain why this is. We're going to explain the control of solubility of ionic compounds on the molecular scale based on our enthalpy and entropy rules, and then from that we'll explain why this comes about. So the picture of the way ionic compounds dissolve is you'll have a salt. So this here is potassium sulfate. What a crummy... Oh, I see. These are sulfates. These are sulfates. These are potassiums. So these are potassiums. Those are sulfates. And when it's a solid, it's this crystal here. When it dissolves, what happens is the ions are surrounded by water molecules. So the potassium ion is surrounded by water molecules like that. And the forces between those are ion dipole forces, because the names of all those intermolecular forces come from the genesis of their charges. And so the potassium has a positive charge because it's an ion. The water's attraction to it is because water's polar, so it's an ion dipole force. And so those forces can be pretty considerable even though they're intermolecular forces, because the potassium's charge is really high and there's a lot of water molecules around it. So a single potassium can make a lot of different bonds to one water molecule. The other thing that happens is when they dissolve, the ions go their separate ways. So the potassium ions start out attached to and not moving from the sulfates, and the sulfates are attached to and not moving from potassiums. And when they dissolve, they split apart and float away from each other. So those are the two things to think about. The ions get hydrated, and the ions go free or set free. So let's look at our enthalpy control first. So our enthalpy control shows that the enthalpies of hydration, so this is making water ion bonds when the salt dissolves. And what we see is that things that have +1 charges or -1 charges, the things that are +1 charges, they tend to be relatively modest. 200 to, like, for lithium, it's pretty small, 500. So the smaller the ions, you'll notice the smaller the ions, the stronger the force. Hydrogen ions are really strong just because they're so tiny. If you look at +2 ions, those forces are actually significantly higher. Instead of being like -2, 300, those are roughly 4 times higher. And it's because it's the charge squared. So the forces of attraction between 2+ ions with water when they go into water is much stronger, and with 3+ ions even more so. So having highly charged ions leads to really strong forces between the water and those ions. And that would say that highly charged ions would be more likely to dissolve. Okay, now the next thing is that entropy control is the following. Hydration number is the number of water molecules constrained by one ion in solution. And so this little picture here says it looks like it would be 4, but in fact it's not. So what happens is a potassium ion will constrain 6 water molecules. A cesium ion will constrain 6 water molecules. But look at this. A lithium ion will constrain 22 molecules. A magnesium, 36. A cadmium, 39. A zinc, 44. So one zinc ion can lead to 44 water molecules not being able to go their free ways. And that's because one zinc doesn't bond directly to 44 water molecules, but the zinc gets one shell of water molecules. Those water molecules get polarized because they're near the zinc, so you get one water shell here. And then that shell attracts another shell. So you can get 2 or 3 layers of water molecules, and you can have a whole slew of water molecules all constrained for that. So what that means is that as larger ions or larger charged ions can lead to a huge number of water molecules being entropy disfavored because they now can't move around. Okay. The next thing is that when ions dissolve, what happened is we have these large enthalpies of hydration. So the ions go into solution and they make bonds to water, and that can be big, but that is largely offset by the fact that the ions need energy to break apart. That is their lattice energy. So the lattice energies and the hydration energies follow the same trends and mostly offset. So I'm going to write that out why that is. Higher charged ions are harder to separate, but make stronger bonds to water. So those two things offset each other. So when an ionic compound dissolves, sometimes it takes more energy to break the ions apart than you get from the bonds with water, and it'll be endothermic. Sometimes you get more energy from the bonds to water and it becomes exothermic. So those largely offset. On the other hand, when ions break apart and the ions go free, what occurs is that there's no change, no preference entropy wise isn't a word, for separating low charged ions versus high charged ions. So separating like a sodium and a chloride from each other has the same entropy as separating, say, an aluminum 3 plus and a phosphate 3 minus, phosphide 3 minus. So separating those from each other would have the same entropy change in terms of separating those apart. But aluminum 3 plus and P3 minus would have very large disfavored hydrations. Entropy effects. Okay, so let's go over that again. So what happens is when an ionic compound dissolves, the ions have to separate from each other, but then they form bonds to water. And those two things are not that far from each other. When an ionic compound dissolves, if things of low charge break apart, the ions go their separate way, and that's favored. And they form bonds to some waters, and that's like disfavored, but not that much. When you have ions of high charge, what happens is the ions break apart entropy-wise, and that still is somewhat favored. But when those largely charged ions go into water, they bind lots and lots of water molecules entropy-wise and get to be very disfavored. So again, the reason ions of high charge don't dissolve very well is because they cause a decrease in entropy of water. Okay, so again, the things that cause that to happen are things that have large charges, like these. And the one thing that's got a minus charge also is really good at binding to water. Hydroxide is great at binding to water. That's why that happens. Okay, so that ends our control of our inherent control of molecular shape with why things dissolve and not. And finally, we're going to go to external control of solubility, things you can do to make things dissolve more. And the first one is a very special case. It's just pressure effects of solubility of gases dissolving in liquids. And this has a law called Henry's law. It has a constant, the Henry's law constant. And what happens is S is the solubility is equal to the Henry's law constant times the pressure of the gas in the air above that liquid. And the higher the gas pressure, the higher the solubility. And so we can use this to calculate the solubility of water, of oxygen in water, under a pressure of 0.2 of 66 atmospheres. We're just making that up. Here's some gas, some Henry's law constants. So this is a funny thing about constants. So notice the constants are different for all these different compounds, and they're at a particular temperature because the solubility changes with temperature. So these are the constants for the solubility of individual molecules at a particular temperature. So there's essentially an infinite number of Henry's law constants because it's different for each compound, and for each compound it's different at every temperature. But if you got one compound and you got one temperature, works fine. Okay, so the solubility for oxygen is going to be 0.66. Oh no, I'll go in order. It's going to be the Henry's law constant, 1.28 times 10 to the minus 3 moles per liter atmosphere, times the pressure, which in our case is 0.66 atmospheres. So I'm gonna get my calculator out. Not been doing any calculating in this this fine little lecture you're listening to. 0.66 times 0.00128. And it comes out to be 8.45 times 10 to the minus 4 moles per liter. That's how soluble it is. Which is not very much, but you wouldn't really expect oxygen to be very soluble because it's a nonpolar compound. This is also an example of that's important for medically. What happens is when someone is like, for example, in a car accident and they lose a lot of blood, one of the things that the EMTs will do is give them oxygen. And the idea is the solubility of oxygen in the air is going to be the mole fraction of oxygen in the air is like 0.21, I think. And so it's around 0.21 atmospheres. So the solubility of oxygen in the air is 1.28 times 10 to the minus 3, 10 to the minus 3 moles per liter atmosphere, and times 0.21 atmospheres. So the solubility of oxygen in just regular air is 0.00128 times 0.21 is 2.6 times 10 to the minus 4 moles per liter. But if you give someone pure oxygen, if you like have an oxygen tank and put the oxygen mask on their face, then it's the solubility is going to equal 1.28 times 10 to the minus 3 moles per liter atmosphere times 1 atmosphere. And so there it's 1.28 times 10 to the minus 3 moles per liter. Even I object to this crappy thing. Oh, sorry, this bad thing here, 1.28. So with pure oxygen to breathe, it's 5 times more soluble. And the idea then is that when you breathe in, your lungs will absorb more oxygen because the liquid in the lungs, the oxygen gets to your cells by dissolving in the water in your lungs. The oxygen will absorb into the water in your lungs and dissolve into the water in your lungs 5 times more, and therefore that's going to shift the equilibrium to allow more oxygen to bind to the hemoglobin. The hemoglobin will become more efficient, and more oxygen will get to your cells when you do that. So, giving someone oxygen when they've lost blood is an example of using Henry's law. Okay, last thing here is the external control of solubility is a temperature effect. And the general idea is that delta H of dissolution is exothermic. That means delta H is negative. Then solubility decreases as temperature increases. And if the delta S, well, this is pretty useless. This is a silly thing. If the solubility, if the delta H dissolution is endothermic, that was wrong here, then the solubility increases with increasing. So if delta H is positive, then the solubility will increase with increasing temperature. So it turns out that all gases have exothermic dissolutions. And the reason for that is that when a gas dissolves in a liquid, you're making new forces, you're making new intermolecular forces, but you're not breaking any forces because the gas didn't have any intermolecular forces. So you're just making forces, therefore it's exothermic. And so an example of this that's really important is that the solubility of oxygen in water decreases as the water gets warmer. And so it's here for something that's near the freezing point, and on a hot summer day, really hot summer day, it's down here. So on a really hot summer day, there can be 40% less oxygen dissolved in the water than there would be on a cold day. And so that has a big effect on things like plants and animals that breathe, particularly fish and animals underwater that breathe oxygen. All right. In most cases, delta H of dissolution most dissolutions are exothermic, and they lead to decreases in solubility. And when it's endothermic, it leads to solubility increasing. That's generally true, but it's not always true. It's not a rule that always occurs. So you can look at, for example, lithium sulfate here is exothermic, so it should become less soluble as temperature goes up, and that's true. But if you look at lithium chloride, it's exothermic, dissolving as well, but it actually gets to be more soluble as temperature goes up. So our general rule here doesn't work, but it works most of the time. All right, and that is the end of this section.